talk is from the Dilip and Rafia, who is currently working in ADB as a principal software engineer and software engineer. They both have very good experience in query optimization, query parallelism. They're working as a developer, and I request them to start their presentation.
Hello everyone. Am I audible? Okay, so today we are going to talk about parallelism in PostgreSQL. So this is the overview of our presentation. First we start with the infrastructure of parallelism in PostgreSQL. Then we'll continue with the intra-query parallelism, what we got in 9.6. We'll briefly touch upon the parallel executor or parallel aware nodes, what we got in 9.6, their performance results and their limitations. And then we'll move ahead to our main part of the presentation, where we'll describe what new we are getting in the parallelism for the V10 or for the future version. And we'll also talk about their TCCH results. And finally, we will conclude with the takeaways. So basically, the infrastructure or the architecture we divided mostly in two parts. First thing is the groundwork for parallelism, which is got developed in multiple versions, 9.4, 9.6, 9.5, and some part in 9.6. And second part is intra-query parallelism, what we developed specifically for 9.6. So in groundwork, we got the dynamic background worker, dynamic shared memory, shared messaging capabilities, group locking, and parallel context. And in a couple of slides, we are going to describe all this in little more detail. And intra-query parallelism, we got some parallel executor node, which are sequence scan, joins, and aggregates. Okay, so I'm going to use this diagram to explain the working model of parallel query, or specifically parallel executor. Okay, color is not completely visible here. So each functional module, each rectangle shows one functional module of parallel executor, and I try to put the modules which are related to each other into same color, and the arrow shows the dependency between the modules. So basically, the rectangle where it starts is functionally dependent on the module, on the rectangle where it depends. So in next couple of slides, we are going to talk about all these modules, but in detail. The right hand side in the purple color, which is not clearly visible, is basically the most basic infrastructure required for the parallelism. And the left hand side, which this part, basically these three modules, which provide the messaging capabilities where the worker and leader can communicate to each other. Because in parallel query we are having multiple workers operating on the same thing, so we need certain communication mechanism. And the center part, the three boxes, the parallel context, group blocking, and state synchronization. These are the core parallelism toolkit, and it is general parallelism stuff, not specifically for the parallel query. And top mode in the yellow color is specifically developed for the parallel query, and that we got in 9.6. Okay, so the groundwork of parallelism in the three part, what you see in the down, if you read the topmost part, all three we put into the groundwork for parallelism, which got developed over 9.4 to 9.6. So first thing is dynamic background worker. So earlier, prior to 9.4, Postgre also had the background worker launching, but that was not dynamically. It means at postmaster startup time, you can get some worker. But as part of that, any backend can request to the postmaster on demand and get some of the worker launched dynamically. And this is the most basic requirement for parallel query to work, because those workers are going to become your parallel workers. Second part is dynamic shared memory. As we all know, Postgre is process-based model. So if we are going to launch multiple workers, we need certain mechanism where they can share the information, share the plan, and communication between the multiple workers. So basically, dynamic shared memory, using that module, we can allocate a raw chunk of memory on demand. And we got the shared memory table of content. Using that, we can divide the DSM or dynamic shared memory into a chunk. And the last part is the shared memory capabilities, shared messaging capabilities. So basically, if you see our backend is directly connected to the client, where it can emit the tuple or error message direct to the client, but the workers, they are not directly connected with the clients. So worker need a certain mechanism, they can send the error information or the tuple to the client. And that is done by the shared messaging capabilities. Through that, workers are connected to the leader through two queues. One is the error and message notice forwarding queue, and second is tuple queue. Next is parallel context. This is the core toolkit for parallelism. The main work for parallel context is to launch a couple of workers on demand, put them into useful state, execute the C code which is instructed for the workers, and timely shut down. So basically when I say putting them into useful state, that means if we execute certain piece of code in the worker, the effect should be same as if I'm executing them in the actual backend. And that it gets done with the help of state synchronization, where we share the same GUC parameter with the workers, we load the same library, we share the same transaction state and same snapshot. And the last part is the group locking. So basically group locking is implemented to solve the undetected deadlock problem. Suppose we consider the worker and the leader as independent entity. It may so happen that our backend or leader is waiting for some other backend, and that backend is waiting one of the worker which is launched in this parallel query. It means that their deadlock detector can never detect a cycle. So it will be undetected deadlock. For solving that problem, we create a group of leader and the workers. We'll put them into a same group, and any member of that group is pointing to some backend, and that backend is waiting for some member of that group. It will consider as a cycle, and we can detect that deadlock. And next part what we got in 9.6, the final, we see the first set of parallel query working. So first one is the parallel executor support. So now we have the parallel context in place, we have the shared memory in place, we have capability of launching the workers. So we only need a way that we can share our plan with the multiple workers and get them execute in those workers. And also we need to share the instrumental information, like for explain, analyze results and all, we need to share across the workers. For that we need to send in instrumentation information also. And the next part is parallel aware executor nodes. So when I say that when we call a node as parallel aware, it means if we execute that node under the parallel context, under the parallel mode, the behavior or the way of execution will be different than if I'm executing without parallelism. For example, if you see the sequence scan node or index node, if it execute under the parallelism, it means without parallelism, means it will have to execute one by one each block. But if I go under the parallelism and execute, it need not to execute each block, it have to get the block information from the shared location and execute that block. That is a basic difference and very simple difference. And finally the gather node. When we are getting the multiple workers are working on the different block and producing the tuples, we need a certain way to emit those tuples either to the client or to the higher node. We need a certain mechanism who can collect those tuples and send it to the centralized location or basically client or higher level node. So that part is done by the gather node. Okay, so this is intra-query parallelism in 9.6, and Rafia will talk about that, and also she will talk about the performance result in 9.6. I'll hand over it to Rafia.
Yeah, so we'll see what are the basic operators that got implemented in version 9.6. So we'll start with the access methods. So it's the first version to have witnessed parallelism in PostgreSQL. So we have only sequence scan, which was parallel aware. Not index and index only scan could be executed in parallel mode at this time. For joins, we have nested loop and hash joins which can work in parallel, but there was no support for merge join again. But the other thing with the hash was that only if the hash table is small enough to fit in shared memory, then only it's advisable, because each worker creates its own copy of hash. So that might not be very helpful if hash is very large. Next is parallel aggregates. So in parallelism, we got split aggregates into two parts. First is the partial aggregate and then is finalized aggregate. So in partial aggregate, each worker does aggregation, and then at the master node, all of these aggregates are accumulated and done the finalized process. So we'll see if we get any improvement on the performance of TPCH benchmark after this parallelism. So the experimental setup at this time which we used was an IBM Power 7 box, which was in community commonly known as Hydra. There was this parameter that time max parallel degree, which is now max parallel workers per gather, which was we kept as 4. Work memory we set as 64 MB and the shared buffer size was 8 GB. Scale factor we kept is 10. So this gives around 15 GB of database. So here is the performance results. The x-axis is for TPCH query numbers. The y-axis is execution time in milliseconds. The red bar here is without parallel query and the blue bar here is with parallel query. So we can see the difference in performance, like for query 1, query 5, and then there are some small variant queries also like query 8, query 19, query 17. So the performance impact is great. We can see it's almost 4 times for many of these queries. But yeah, we can see there are certain queries like query 9, like query 16, 4, not very much. It's okay, they might be using a little bit of parallelism, but still maybe they want certain more things which we have not yet provided. So let's see if we got figured that out. So on seeing their query plans and studying them, we found that we need parallel index scans or index only scans, particularly for query 6 and 14. Then for parallel bitmap heap scan also your query 4 and query 15 might be able to use in certain settings. So we thought of like maybe we need that. And then parallel merge join. So as we go on increasing scale factors, parallel merge join comes to be a more favorable operator, because in TPCH queries we have many group bys and order bys, and which is expected in OLAP behavior. So we need parallel merge join. Also parallel hash join was not doing great benefit because each worker was creating its own hash. So maybe if we'll have a shared hash that all the workers build together and then we can use it. So we got an idea that maybe we need certain more improvements there. And also if there is some subquery, init plan, subplans sort of a thing, then nodes cannot use parallelism. So we need to figure some way out there itself. Moving on, just to give an overview, what were the limitations at that time? There were many forbidden operations, like for cursors, for triggers, we do not really want parallelism because it might not be very helpful in all cases. Also, for serializable isolation level, we do not provide any parallelism support. And there were many parallel unsafe functions which introduce some transaction state change. So then it will not be feasible to have parallelism in the current infrastructure. There were certain restrictions that were there because it was the initial version of parallelism supported PostgreSQL. Like we have init plan or subquery scan, as I mentioned before also. So nodes using them cannot use any parallel scan modes. So we might need to think over this, and then if you have temporary tables, CTs, foreign scans, then also parallelism is not supported. Other than that, there are certain parallel restricted functions which were which were using mostly scan or these restricted operators, so we cannot parallelize them also. So after studying all these limitations, what can we expect to come in parallel PostgreSQL? So first is that we need certain more access methods like parallel index only, parallel bitmap. So index and index only are already committed, so we are likely to see them. Other join methods also need to be there, like parallel merge join has to be there, which I think is under patch, under revision and all. Then we have a hash join with parallel hash build also underway. Then we have one new node that is gather merge. So when we gather nodes from after scans, we might not be able to save their order. So to save their order, we have this new node called gather merge. Also, we had some work done in the relaxation of subplan when used by some scan nodes. So for that, if the plan is uncorrelated, subplan is uncorrelated, then we have that restriction removed now. But for init plan and correlated subplan, things are still underway. Also, we can see in coming versions some improvement in parallel append. Apart from these parallel executor nodes, there are certain other parallel commands also, like parallel DDL and maintenance, which are parallel index creation and parallel vacuum. But in the interest of time, we might not be able to talk about these things. We'll only concentrate about executor nodes in this presentation. And now Dilip will take over to explain you these all new operators in detail.
So now, hello. Now we'll talk about each operator what we are getting developed in for V10 or for the future version in a little bit more detail. The first part is parallel index or scan. So as Rafia told, till 9.6 we have only sequence scan is parallel, which is not really good. We want more method to be in parallel, because generally if you see the industry, the index is most useful operator and that should be in parallel. For getting the index scan in the parallel, this is a design what we followed in Postgre. There are many other designs and many other vendors might be using some different way of doing that. So first, the first worker who reaches to the index will scan the P3 from the leaf from the top and reach to the leaf where the rank starts. And once it reaches that position, it will wake up all other workers and then they will jointly scan the leaf pages of the index. Yes.
At least now only the sequential scan is parallelized.
Till 9.6, only sequence scan is parallelized.
Can I get one information? If I use index scan
Yes.
and sequential scan for the same table using parallel scan, which is faster?
That depends upon how much data is getting selected. Suppose you are getting 80% data selected, then maybe sequence scan is faster and parallel will be even faster. And suppose it is very less number of data, only 10%, then we can get competition between the index scan and the parallel sequence scan, whichever based on cost is really faster.
So in that presentation, some of advantages were there. Those advantages are only based on sequential scans. Seems.
Till 9.6, that parallelism advantage is only based on sequence scan. But we are getting more for the parallel index and parallel bitmap. We are just going to talk about. So when the data fit into the memory, that time the parallel index scan will perform really well, because we are getting the parallelism benefit mostly from the CPU, not from the disk. So if there is a random page fetch and a lot of disk access is there, then maybe the improvement will be there, not in the multiple of 2x or 3x, but it's completely in memory, no random page fetch, then we can get the complete benefit of parallelism. We can see in the multiple of x. And similar mechanism we follow for the index only scan as well.
Are you doing this only for B3 indexes?
Yes. As of now, we are doing only for the B3 indexes. We can, maybe in future, we can think of changes and some other indexes. I'm not sure for hash it will be really useful. Next is parallel bitmap heap scan. So generally when I talk about people, talk with people about the operators, they are more sure about the sequence scan, where it is used and where the index scan is used, but many people are not aware about when the bitmap scan is used. So before starting how we implemented the parallel bitmap scan, I just want to introduce what is bitmap operator and where it is used. So generally we say when the huge data is getting selected, suppose 80% of data is getting selected, we generally go for sequence scan. If it is very less, 10%, 15%, we want to go for index scan. What about when it is come to 40%, 50%? We don't want to scan whole table because we are wasting our effort, because we are interested in only 50% of tuple, but we are scanning 100%. But if you go for index scan, we need, for every tuple, we need to fetch a random page, because we are not only interested into the index tuple, we may need to get the heap tuple also, and we need a lot of this page and random page fetch if data is not fit into the memory. So there comes the bitmap scan. So basically, we do the index scan first, we collect all the tuple ID, store it to the bitmap, and finally, once bitmap is ready, we sort them into the page order, and then we perform the heap scan. So finally, we get only the pages which we are interested in, only tuples we are interested, and we just scan the heap pages for those interested tuples. So now I'll talk about how we have implemented the bitmap into parallel. So first, node which reach to the bitmap heap scan will create the bitmap, which we call as a leader node, which will create the bitmap, sort them into the block order, and finally wakes up all other workers, and worker will jointly perform the heap scan, whichever page is selected or whichever tuple is selected in the bitmap. And there is also scope of further improvement. We can combine the parallel index scan benefit, what we see in the previous slide, and we can prepare the bitmap also in the parallel, and then we can perform the heap scan in parallel. We can combine both the benefits basically. So this is how the parallel bitmap plan may look like. You can see I have taken one of the plan where the bitmap or node is there. It means there is multiple index on two different columns, and you can generate a bitmap for both the nodes and combine them. You can have bitmap or node or the end node, depending on your condition. And finally, the bitmap is ready. The finalized bitmap can be used by multiple workers to scan the heap pages. Yes.
Previously, you said the parallelization works only when the data fits in memory.
No, I told it can give a huge benefit when it is in memory, because we are getting the benefit out of the CPU cost, not the disk. The disk IO is still the sequential, not the parallel.
So the planner makes a trade-off where if the IO cost is more, it doesn't go for parallelization.
It will calculate. If IO cost is more and if CPU cost we divide by how many workers we have, and if we don't get the better plan for that, because we need to divide the CPU cost, plus we need to put the cost for gathering the tuple at the leader. If it comes higher, then we will not go for the parallelism.
Because I have one more question, because if
Yes.
you say it brings into memory, which memory are you referring to? Shared buffers?
Yes, shared buffers.
Because shared buffers has a mechanism where it doesn't allow sequential scan because it blows up the whole lot of memory.
You know that?
No, when you do a sequential scan, only 256 KB of the tuple will come into shared buffer. Right? So when you say whole of the data fits into shared buffers, I don't correlate how that works.
You can increase your shared buffer. But actually, the current planner is not don't calculate how many shared buffer you have. It will calculate only your work memory.
No, the shared buffers has something called a ring buffer. It has 8 KBs of. It has 8 arrays that totals 226 kilobytes of space. So when you do a sequential scan, it doesn't come into memory. Only 8 KB comes into memory.
Yes, but you can increase your. You are telling the complete sequence and then you do your ring buffer of that much size. Yes, that's true. Yes.
Need not come to the buffer.
Yeah, because of the complete table scan when we do, it will only use that ring of that, so we don't remove all the tuples from the memory and all the pages we pull it out. So next is the parallel merge join. When we told that when we go to higher scale factor and the top level node is interested into the order of the tuple, that time the merge join can be really useful. And for when the V10 we have got the merge join also in parallel, means it's under progress. So basically the outer side of the merge join will do the parallel scan, and inner side will still be built completely by each worker. Every worker will build the inner side of the sort, or it will perform the complete index scan or the materialized node. Only the outer part will be in parallel. The same thing what we got for the hash in V9.6. And there is also scope of improvement that inner part also we can build in parallel by multiple workers, and then we can perform the first inner part we can build in parallel, then we can perform the outer side in the parallel. And so next is parallel shared hash. So far in 9.6 we have got the only outer side of the hash in parallel, and inner hash will be built by each worker. So which is particularly good when your hash table is very small and it can fit into the work memory. But in case it does not fit into the work memory and there is a lot of batches which goes to disk, it's really difficult to get good performance improvement. Suppose inner part is 50% of, it's taking 50% of time of the total hash join. it means you are solving only the 50% of problem. So if you bring that to 0, still you will get only 2x improvement. And I think when it comes to performance, we are a little greedy and we are not satisfied with the 2x, we want more. And for that, we can employ all the workers first to build a shared hash. Whichever batch first we want to probe, we can employ all the workers, build the hash, and then we can do outer joining parallel and probe into the same shared hash. And that will be, now if you bring it to 0, it can be any x. And that also we get the parallelism in both sides of the hash table. So far we got only the outer side, now it's on either side of the hash table, hash join.
So the hash table is in shared memory, right?
Yes, till 9.6 hash table was the local hash and every worker is building their own hash. But as part of this work, what I talk, the hash table will be created into the shared memory.
Instead of work memory.
Huh?
Instead of work memory.
It will, yes, it will be shared memory, but the amount of shared memory we will use is equal to work memory of multiple workers. Suppose 3 workers are there, we take 3 into work memory and we'll create the hash into that. And that will be created by multiple workers. This is how the plan will look like. The outer side is using parallel sequence scan, that is parallel, what we have seen in 9.6 also. But now inner side can also use the parallel sequence scan and build a parallel shared hash.
You allocate 3 into workmen for in shared memory, right?
Number depends upon number of workers. Suppose 3 workers are operating, then we allocate 3 into work memory into shared memory, dynamic shared memory.
Even before creating the hash table itself, we allocate.
No.
That yes, that much work memory we can use. So
No, work memory is a PostgreSQL initial setting.
yeah, we are actually.
You can take it offline.
Yeah, we can take this question offline. And so next part is the gather merge. So previously we have talked gather can only gather the tuple and emit it to the higher level, but it don't take care of the interesting order. So instead of that, we got the gather merge, which is another option to the gather. So wherever we needed a sorted order or interesting order, we can collect the tuples from multiple sorted streams and only emit the tuple when we are sure that it is the shortest tuple among all the streams, and we can hand it over to the top level node. So I think that's all about the gather merge, and I'll hand over it to Rafia for discussing the result of the PGCH.
Since I'm told the time is very less, so I'll try to cover it as fast and as parallelly as possible. Let's see if I can improve some performance here itself. So this is the experimental setup. So apart from the basic things that I did, was that additional indexes we introduced in TPCH, and also we experimented with more scale factors. Previously we had a small scale factor 10, now we have moved till 300 to depict if it's really scalable operator. So here are some results from 20 scale factor for access methods particularly. So we can see, as expected, query 6 and 14 are using parallel index and are showing good improvement in performance. And for parallel bitmap also we have one query which is showing good performance in these benchmark queries. And these get all the more when you move to higher scale. And for parallel shared hash in particular, we have this query which was query 9, which was previously not affected in terms of performance by the added parallelism of version 9.6. But now if we get this patch also, then this is almost 2x improvement in performance. Similarly, other queries like query 21 and query 7 are also showing good improvements. But yes, there are certain queries which are not really affected by the additional operators also. So I would like to point that these are very small running queries also. So maybe parallelism is not very good for these queries because they don't have that much of data to operate upon. So just wanted to specify that. In total, when we go to, with all the patches on 300 scale factor, we can see that we have great benefits in query 3 particularly, in some high running queries also like query 15 and query 22 also it is showing good performance, but it is itself a small running query. Query 6 we already pointed out. So we can see that we got some more improvement in performance with these additional operators, so effort doesn't go waste like that. So how to further improve our performance when using parallel operators? So there are certain parameters that we might need to have a check upon while using parallel query. So one is max parallel workers per gather. It should be set appropriately depending on your actual hardware, but we recommend around 1 to 4 in general scenarios. Other costs are like parallel tuple costs, setup costs. These also depend on your architecture. So if you have a high CPU configuration, then you might want to set it very low because current default configurations are high enough. Similarly, if you really want your table to be scanned and you feel like it is because minimum parallel table scan size is set to be too high, you can set it lower. And similarly for index scan, if you really want some table to be done in parallel even though default values doesn't say so. Other thing is random page cost is because we are having in-memory database, so it is set quite high and we are not paying any random access disk cost, so it should be set lower. Other more popular operators that we already know mostly are work mem, effective cache size and shared buffers. We might need to set their values appropriately depending on your database size and your machine configuration. So, but still there are certain scenarios when we also, like parallel operators also do bad. One is that when as per the planning the number of workers are not launched. So in that case you might want to increase max parallel workers so that if multiple queries are running in parallel, each can get the number of workers planned. The other thing is shared buffer size. This is quite important because planning time he might expect that the memory is available, but at runtime it is not. So you have to have this higher value so that your inner side of join mostly gets fitted in memory and what other the things you need there. Similarly, random page cost. So maybe your data is not in memory and you have set random page cost to be too low. So make sure that your database is in memory. And then if you are setting it too low and your database is in memory, then effective cache size should also be set accordingly. But still there are situations where almost God also cannot help, and these situations we call as underestimation in selectivities or wrong estimation of selectivities. So there every planning goes wrong. So to conclude this presentation, what we saw is that once we introduce parallelism in PostgreSQL, now our concentration shifts to an extent towards OLAP queries also. So this is a good shift, and makes it more popular, I hope. And the other thing is that in version 9.6, we saw a few operators, but still on benchmark also, and otherwise also, we saw that the improvements were great. Out of 22 queries, 15 were using parallel operators and were showing good improvements. Like around 3 queries were showing 4x improvement, which is just great. And with the upcoming versions, we will see more parallel operators, parallel index, index only, all we talked about. So here also we can see that now in 22 queries, 10 are using these additional operators and are showing good performance. Like around 4 of these queries are showing 2x improvement, which is again great. So thanks a lot for your time and patience, and I think I'm on time.
No, just one question. Test setup. You mentioned that 32 cores and 512 MB RAM.
I think it's better to take out offline. Because
How many processors?
Sorry?
How many processors were in that?
So, okay, we did a very federal setup, just one server, one client, and that is it, and no other process was running in parallel.
How many physical processors in the system?
Oh, physical processor. Oh, the system is having.
Is 32 is out of one processor or it's multiple?
No, it's total.
That makes a lot. That makes a lot of difference in PostgreSQL.
Yes,
Because
yes.
four physical nodes are there in the machine.
Yeah.
The 32 cores.
Thanks. Thanks, Rafia. Thanks, Dilip.
Thanks.